There is a very common and popular explanation of the second law of thermodynamics, allegedly coming from a statistical formulation of thermodynamics. And so what we are going to see in this video is that actually this explanation is fallacious. So the reason why I bring up this particular explanation of the second law is because in the last 4 weeks there have been 2 videos by very influential physics YouTubers and professional people who are Sabine Ossenfelder here and also Derek from Veritasium. The thing is that both videos discuss the concept of entropy and how a statistical interpretation of entropy leads obviously and inevitably to the second law of thermodynamics, or to an explanation of the second law. Now, these particular explanations rely on 2 formulas, which are the entropy formula, S, where S is the entropy, is equal to Kb log of omega, where Kb is some constant called the Boltzmann constant, and log of omega is simply the log of the total number of states, or so-called microstate, comprising a specific macrostate. And then you've got some probability, which is going to be simply 1 over omega. So I'm just going to try to explain what is the argument they make. My explanation or my drawings and examples are going to be taken from something quite similar to what Sabine Ossenfelder, so the physical system is closer to the one Sabine Ossenfelder looked at, but the explanation is going to be discrete and therefore closer in the calculations to what Derek has been showing with some kind of energy distribution things. So let's see what it is that I'm talking about. So let's say, for example, that you imagine a system of 8 particles, and instead of moving continuously in space, they are bound to move on a grid. And you're going simply to count the number of states of your system simply by counting how many ways you've got to put the particles on the grid. Now, the current depiction I have here is basically that you've got a box that has been split in 2 by a wall, and the wall is represented by a white line here, and so the 8 particles I've put in the box here are only able to move in the 6 times 12 available sites. So in essence, you've got 8 particles that can move on 7 to 72 sites. And what that means is that if you look at this quantity, which is the set of all possible 8 particle configurations you can do in the 72 site right-hand side of the box with a physical wall separating the 2, then what you're going to get is that the number of possible configuration is a combinatorial term, which is 72 factorial divided by 72 minus 8 factorial, and then times n factorial. And that's so-called like the number of ways to pick 8 sides out of 72. Now, the number you're going to get here, I'm just, I'm taking here a rough estimate. This is not the exact number, but it's basically about 12 billions. So you've got 12 billions possibility already with simply 8 particles to be put into 72 sites. Now, if you look at the corresponding entropy, and if I follow the rule of S equal Kb log of omega, you're going to get that the entropy is about 23 Kb. Okay, so that's a much more manageable term, and that's why people use entropy. At least that's one of the reasons why people use a statistical entropy rather than omega, for example. Now, what you can ask yourself is, what happens if you remove the barrier that was preventing these particles to move? So in this particular case, you are going to have 8 particles, still the same ones, but then you've got 144 sites that are available. The thing is that, as we know, if we imagine, for example, that this is a model for a drop of ink or something that is spreading in water, then we know that somehow we are expecting that over some time this is going to reach some kind of uniform distribution overall. And so how do we represent this? So one of the things we can ask is we can consider in fact a split configuration where we've got the same number of particles on each side, so on the left side and on the right hand side, and I've put here a virtual, so that's a virtual divide which is basically halfway through the box. But this is really a virtual one, so this is not a real one, this is just one that I've put for as an aid for your eye to see what I'm looking at. So essentially you've got 72 sites per side and 4 particles per side, and this tells us about a class of configurations that I'm going to denote that way, which is a class of configurations where you've got 4 sides on the left and 4 particles, sorry, on the left and right hand side respectively. Now you can try to ask yourself, okay, what is the number of states in that case, and you're going to find that this is simply 72 factorial divided by 68 factorial and then times 4 factorial, and then the whole thing squared, because you've got now 2 sides to consider. So that's going to be the number of states, and what you're going to find is that it's about 1.1 trillions possible microstate or configurations here. And if you look at the entropy this corresponds to, you're going to find that this is 28 kb, and you can say, obviously, rightly so, that this is 28 kb is larger than 23 kb. So from that point onwards follows the conclusion of both Sabine Nossenfelder and Derek, which is the following from Veritasium, which is the following one. It basically says, well, look, we've got actually more states in the second configuration where you've got a uniform distribution of the particles on the left and on the right, and then if you were to have all the particles on the right hand side, for example. And so what we find is that, well, because there are more states, then it's more probable, and therefore there is a higher entropy. Okay, so and that's what we find indeed, that there is a higher entropy indeed. And so what they say is that therefore this explains the second law, and essentially we can just say that the second law simply says that you're going to move towards more probable states in your system. So that's kind of the statistical explanation that is provided in these 2 videos, and of course I'm going to put the links to these videos. I encourage you to watch them. They are in any case very well made. However, I disagree with this particular point on entropy. So the thing here is that this is actually incorrect. So this is not correct that this particular reasoning explains the second law. And I'm going to try to clarify why this is the case. So the first point is that these 2 formulas, S is equal to KB log of omega and PS is equal to 1 over omega. PS here is a probability of a particular state, so configuration, if you will, to occur, or so that would be a configuration of particles, but that can also be a class of configurations, okay? So a set of configurations to occur. This is only true and valid at equilibrium, okay? So in what people call statistical mechanics, these 2 formulas only hold not only at equilibrium, but they also hold in certain circumstances with like isolated system and so on and so forth. So there are plenty of constraints within which these 2 formulas apply, and in fact these 2 conditions were not specified really in the 2 videos aforementioned. And by the way, this argument is also put forward in many textbooks, and I think they confuse the reader more than anything. So they only valid at equilibrium, but then the problem is that if you look at the two cases we looked at, they correspond to two different equilibrium situations. The first one, you've got a physical barrier that completely prevents the particle from moving from the right-hand side to the left-hand side. So it's a physically completely different experimental setting. And then on the right-hand side, instead, the particles are free to move wherever they want in the box, and we simply put a virtual demarcation halfway through the box to discriminate the left-hand side from the right-hand side and look at specific collections of possible particle configurations. Okay, and so these are completely different equilibrium situations. So to put that in perspective, consider, for example, the fact that because they are different equilibrium situations, they are going to correspond to two different equilibrium probabilities. So let's go to our initial case. So we've got 8 particles that have to roam, if you will, in 72 sites. Now, if we consider then our collections of all possible states with particles that have that are all on the right-hand side, in this particular case, guess what was going to be this probability? Okay, so probability for all the particles to be on the right-hand side in this particular equilibrium situation. And in fact, even outside of equilibrium, I'm sure you understand what that is. This number is actually 1. So the probability for all the particles to be on the right-hand side, given this particular experimental situation, is exactly 1. Okay? Now, a completely different scenario is the following one, is you actually let the particles move wherever they want because you've removed the actual wall, and you look at what is the equilibrium, and I insist on equilibrium here, the equilibrium probability for all the particles to be on the right-hand side of some kind of virtual divide. So now you're asking for something completely different. The particles are allowed to move wherever they want, but then you put a virtual divide there and you say, what is the probability for them to be all on that side? It's very similar to asking what is the probability for, let's say, the 10 first throws of a coin out of 15, for example, to be all heads, for example. So that's very similar to that. And so if you actually do that, you find that the probability now is not 1, and it's going to be 12 billion over 3.8 trillions, that this is give or take. And so, of course, this is a bit difficult to manage, but if you take the ratio, you're going to get this is about 0.003. So that's the probability for obtaining this particular class of configuration, so all particles on the right-hand side when they are available to move, or when they are able, to move all over the place. So that's a probability when this particular equilibrium has been reached. Now, if you consider the other particular case, then you will find that the probability is about actually 0.3. So that's the probability at equilibrium, so when they are free to move about everywhere they want, you're going to find that the probability of all the configurations, so for the same number of particles to be on the left and on the right, so the uniform configuration, is going to be about 0.3. So that's what matters here. You're going to find that the probability is about 100 times larger to be in a sort of uniform density than if it's not uniform density at equilibrium. So what is the take-home message? Well, the take-home message is that this particular derivation is a derivation that holds at equilibrium. And so when people do that, what it is that they are actually doing, well, they are not explaining the second law of thermodynamics, because you can't compare two different probability spaces. So they are simply comparing probabilities that are, orange and tomatoes, right, or orange and apples, right? So they are comparing two different things, and that doesn't make really any sense. What they can compare, however, are probabilities for specific collections of states to happen within the same equilibrium situation. Okay, and so what we see is that the statistical interpretation of thermodynamics allows for actually all the particles to be, if you want to, in a corner of the box, and that's actually possible. So that's what people do. They try to explain how you can make compatible the possibility of having all the particles in one corner of the box, while at the same time knowing that in practice we expect these particles to be mostly uniformly distributed and put in place, okay, in space. So that's basically the idea. Now, what is therefore the explanation of the second law, or a statistical explanation of the second? Well, I don't know. Okay, so that's kind of the point. Essentially, if you want to have a proof or a derivation or an explanation of the second law, most of the time you need to replace it by another postulate of the same nature. For example, there are some connections that can be made between information and entropy, and in fact Sabine Ossenfelder does discuss this, and she does it very well, so please again have a look at her video. But in that case you need to say that there is some mechanisms that happen in nature such a way that essentially we lose information over time, and this loss of information is going to increase or make the entropy of the universe overall kind of increase. So that's the bottom line here. Essentially, the commonly used explanation of the second law doesn't work. This is something that is purely made to make compatible two apparently incompatible statements, which is about, again, the possibility of having all the particles in a corner of the box in what we call statistical equilibrium or statistical thermodynamical equilibrium. And the practical experience and empirical experience that these particles are observed to be actually distributed uniformly across space. Okay, so that's it. If you've got any comments, by all means, do let me know in the comment section, and if you liked, well, please let me know. And I see you in the next video.